network infrastructure. By that, we're talking about the different and various network devices that exist on a network and the function that they provide, the place that they would be set up in the network as well. Two of those are going to be switches and routers, and so we'll spend a couple of topics looking at all the functionality provided by network switches, as well as all the functionality provided by network routers. Then we'll look at some additional network devices, voice over IP, firewalls, load balancers, etc. And finally, we'll look at some of the common data center architecture for your enterprise organizations. In this first topic, we're going to be dealing with network devices and the functionality that they provide and how that relates to the OSI reference model. Some of these devices are going to be a bit historical in terms of the fact that they're not really used in a modern network. Others are going to be more common today, like switches and routers. So let's get back to the general concept of networking or internetworking. It's just defined as technology and devices by which computers can communicate across differing types of networks, right? The whole goal of networks is to connect computers and servers for the purpose of sharing resources, data, applications, etc. In order to do this, you obviously do need the clients and the servers and the network interface cards, but you need then networking devices to provide that connectivity. Clients aren't connected directly to servers. Servers are typically not connected directly to one another. They're connected in through a network device. Remember, the Ethernet standard defines a physical star topology and a logical bus topology. So physically, they're wired through central devices like hubs and switches. Then logically, they communicate on a baseband signal using CSMA-CD as the access method. That's all information that we've already gone through. Now, four of the most common types of networking devices have traditionally been hubs, switches, bridges, and routers, and those are the ones that we're going to primarily go through. Networking devices work at a specific layer of the OSI reference model, and the layer that they operate in and the understanding of that model helps to identify not only the purpose but also the capabilities of that device. So the OSI reference model is far more than just a conceptual model. Although it does serve that purpose, it can assist us in understanding network communications as well as the functionality of a particular network device, because network devices are associated with a particular layer, and that means they assume certain capabilities. We think of layer one, the physical layer, and we say that, well, that's really just all about bits, zeros and ones being sent from one machine and received by another system. So they lack so layer one devices would be network devices that operate at the physical layer, and they lack any sort of forwarding intelligence. They just pull in bit streams and push out bit streams. That's all they do. Layer two devices, well, layer two is where the data link layer in the OSI reference model, that's where the MAC address lives. And so layer two devices are capable of selective forwarding based on those physical MAC addresses. Okay, we can decide whether to forward a packet to host A, B, or C based on the MAC address that's in the packet. Layer 3 devices are capable of even more advanced forwarding because that's going to be based on the protocol addresses. Okay, so that's the network layer or the internet layer in TCP/IP, and it's going to forward traffic based on IP addresses. All right, so there hopefully you see how the OSI reference model kind of determines the purpose and capability of that device. Here's a look at the OSI reference model and how these lay out. So physical devices are going to be hubs and repeaters. Okay, data link devices are going to be most commonly the layer 2 switch in modern networks. Older networks might have used bridges and switching hubs. And then the network layer is going to be a router, always, or a layer 3 switch. A layer 3 switch is a switch that technically operates at both layer 2 and layer 3 and is capable of both types of forwarding. So let's start with physical devices. These are the devices that operate at the physical layer. They're simple devices. They have no ability to intelligently forward data. So therefore, a couple of things to know about layer 1 devices. They don't provide network segmentation of any kind. It will just simply forward packets from one system to another. And in simple and especially small networks, layer 1 devices can be used to connect systems very easily and without issue. The issue really becomes due to the fact that they don't provide any network segmentation. They don't segregate the bandwidth. All right, and so if you have 4 devices connected to a layer 1, 4 computers connected to a layer 1 device like a hub, when the hub receives those packets, it's just going to push the packets out all ports. It doesn't try to determine who it was for. So you have a lot of unnecessary network traffic at that point, or otherwise known as congestion. Okay, more nodes fighting for the same type of bandwidth. So, well, if that's the case, then what's the purpose of this? Well, basically just to extend the range of a signal past the limits of a particular architecture. Okay, Ethernet has a hard limit of 100 meters, 328 feet. That's between the device and the central connectivity, between the computer and the central connectivity device. So by using a central connectivity device, you can technically expand across those, because not only do they forward the packets, but typically they would rebroadcast the packets at their original strength. The most common layer 1 devices are going to be repeaters, hubs, and network interface cards. So we've talked about the network interface card. Here's an image of a couple of those. One's Ethernet, the other one's a fiber optic type of card. The NIC is used by clients in both wired and wireless networks to connect to network devices. These cards are typically integrated into a modern motherboard. They can also be installed via a PCI Express adapter card at this point. Obviously, historically, those were, straight PCI, PCIX, different kinds, but now it's all PCI Express. Typically, the NIC is going to be part of the motherboard, and unless I need some enhanced capability like 10 gig or 40 gig Ethernet, I wouldn't need to install a card. Or if I have a wired Ethernet card that's embedded on the motherboard, but now I need wireless capabilities. So if I need something other than what the computer automatically has, I'm going to need to set up another NIC. The NICs have a MAC address that is embedded on them. It's embedded on a flash ROM chip, and it serves for communication purposes. The NIC has to be matched to the media type and to the network architecture as well. So the cable type, Ethernet architecture, etc. NICs can transmit in either half duplex or full duplex. That's an important term for you to know. Half duplex simply means you can send and receive, but only one at a time. So like a walkie-talkie. Okay, whereas full duplex is you can send and receive at the same time. And that would be more like a phone conversation, right? You and I can talk. I don't have to wait for you to stop talking. I can actually talk right over you. There are different channels for sending and receiving. Now, typically with clients, we don't see full duplex NICs, although it's possible. Full duplex NICs are more important on a switch, or on a server, I should say, and they have to then also be connected to a full duplex port on a hub or a switch. One of the most basic internetworking devices is a repeater, and it simply boosts the electronic signal from one network cable segment or wireless LAN and passes it on to another. When I say cable segment or wireless LAN, those would be two different kinds of repeaters. A physical Ethernet repeater would be used to extend the maximum cable length. A physical wireless repeater would be used for the same thing. It would just be retransmitting wireless signals as opposed to the electrical signals on a wire. So repeaters are typically, like I said, they're going to I shouldn't say typically, they're always going to connect similar media. So Ethernet on both sides, coaxial cable on both sides, that kind of thing. And they're just simply to regenerate the signal. Now, there are a couple different repeater types. An amplifier is a repeater that amplifies all incoming signals, including any sort of noise. Those aren't used a whole lot today, just simply because they suffer from extraneous noise on the wire. Signal regenerating repeaters are more intelligent. They read the original signal, and then they create an exact duplicate of the original signal, and they have the ability to then eliminate that noise. Wireless repeaters are probably your most common type to even see in today's networks. Ethernet repeaters typically aren't used. That was more of a thing back in the coaxial days, which had shorter, well, actually, coaxial had longer distance limitations, but in a bus scenario, you're dealing with the maximum size of the physical topology. Whereas when you use star, you're really only dealing between node and central connecting device. So it's less important to have repeaters. Fiber, you certainly would see repeaters with fiber extending past the 500 meter limits for multi-mode, the 2 kilometers and more limits for single mode fiber. Whether you and I will see them depends on really our role in networking. In a lot of organizations, no, you're not going to see fiber repeaters, but they may be used for backbones. The original device that was used to connect multiple computers in the Ethernet star topology is the hub. Okay, we see a very simple little Ethernet hub here in the image. They can connect devices that use either the BNC coaxial connectors or RJ45 connectors. These are extremely inexpensive and they're useful for small networks. They're very easy to configure. You simply connect the devices and then assign IP addresses that work together, or use automatic private IP addressing if you just need a small little network with no internet connectivity. If you need internet connectivity, the hub would need to be connected to a router or something that was providing DHCP addresses and a default gateway. So they're very easy to configure because they don't intelligently forward packets. However, that's the downfall because they broadcast packets out all interfaces. There are two basic types of hubs, two basic categories, passive hubs and active. Passive hubs do not extend the range of the signal, whereas active hubs will repair weak signals and regenerate. So they're like that signal regenerating or intelligent repeater. The latest hubs can provide additional capabilities. When you see things like switching hubs, intelligent hubs, that usually alludes to them having some type of forwarding capabilities, which actually, based on our previous discussion, kind of moves them out of layer 1 and into layer 2. Now let's talk about data link filtering. Based on the functionality of the data link layer of the OSI reference model, the devices that operate at layer 2 will perform filtering based on hardware addresses, MAC addresses. So layer 2 devices then have the ability to create separate collision domains. And we've talked about this. We've talked about the fact that Ethernet uses a contention-based access method. So all nodes are fighting for the use of the same bandwidth. And the larger your collision domain, the less efficient it's going to be. Because the larger the collision domain, the more people fighting for bandwidth, the more inevitable collisions we are going to have, and the more time it takes to actually distribute packets. Bridges and switches are layer 2 devices. They both create separate collision domains on each interface. When a packet hits an interface, it's only forwarded across the interface if the destination node actually resides on that segment. All right, so a switch gets a packet in port number 1, and then it looks at a MAC address table to determine where this packet was actually supposed to go. Okay, and if the packet is actually supposed to go to port number 4, it only sends it out port number 4. It doesn't bother ports 2 and 3. Okay? Same thing with a bridge. We'll see smaller number of interfaces. But layer 2 devices is very important. They do not provide segmentation to create additional broadcast domains. Remember, the broadcast is when you send a network packet out that's supposed to go to all recipients. A hub, a switch, a bridge will all treat that the same way. They will forward it to everybody. Okay, bridges and switches, if it's point-to-point unicast traffic, they'll only forward it to the node that needs it based on the information that they have in comparison to MAC addresses. But if they get a broadcast, they will send it out. Okay, that's just important. Collision domains versus broadcast domains, and I know we've already mentioned that. So bridges are internetworking devices that connect to different LANs, and it makes different LANs appear to be one, or segments a larger LAN into 2 smaller pieces. Bridges are like a router in the number of interfaces that they have. So like in this case, this bridge probably only has 2 interfaces. but it's used to make sure that traffic that's on the first LAN segment never goes to the second LAN segment unless it was destined to go there. So when the bridge gets the packet in that interface, it looks at the MAC address and it says, if the MAC address resides on the first LAN segment, I'm going to leave it there. Okay, I'm not going to do anything. I'm not going to forward this traffic. If, however, the MAC address resides on the second LAN segment, then I will selectively forward that over to the LAN segment. Bridges are at layer 2. They're transparent to higher layer protocols. They can filter traffic based on addresses, but in reality, these are very uncommon in modern networks. The whole purpose, the function of the bridge was really back in the Ethernet hub days, where we had these hubs that weren't selectively doing anything. They were just forwarding everything, huge contention but domains. You throw a bridge in, you at least divide it into 2 collision domains. Okay, you throw a bridge with 3 interfaces, you divide it into 3 collision domains. So it cut down on the collision domains, but not nearly as much as a switch would do. The switch is sometimes referred to as a data switch or layer 2 switch, and it's generally a more modern term for a multi-port bridge. Okay, it operates at the data link layer, and it basically functions like a bridge does, forwarding traffic based on MAC addresses. The difference is the switches have far more ports. That's why I call them a multi-port bridge. Switches come in 4-port, 8-port, 12, 24, 48-port switch varieties. And each of those ports is isolated. So the switch can isolate conversations between ports 1 and 4 at the same time that a conversation is happening between ports 2 and 3. This creates multiple collision domains. Now remember, network broadcasters still sent out all ports, and so they don't provide extra broadcast domains, but it does greatly increase performance. It's night and day comparing a hub to a switch in relation to collision domains. Switches can also provide some additional filtering techniques to optimize performance. Now there is a type of virtual switch. A virtual switch is a software switch that provides similar functionality, but they're using virtualized systems to communicate over virtual network connections. These are used in virtualization. They're also used in cloud computing. So that's something to be aware of. This might just be something as simple as a vSwitch in Hyper-V or VMware. In cloud technologies, we can actually create virtual switches that mimic physical switches from a management perspective. So now that we've covered just kind of network devices in general and hubs and bridges, we're not going to come back to those, but we're going to spend more time on both the network switch as well as the network router. And in this topic, it'll be the switch. So let's start with just looking at some switch categories. Now, you certainly could throw in a category of layer 2 versus layer 3. Just understand that's solely based on the functionality it's providing. Okay, does it only do layer 2 switching, or does it also do layer 3 switching? And the difference is layer 3 is going to be based on protocol addresses. It's going to be more associated with virtual LANs, VLANs. Okay, so a switch, a layer 2 switches, just standard, older switches, those typically are going to fall into the unmanaged, but there might be some that are managed. The layer 3 switches are all going to be managed or possibly web smart. So I mean, you can see how the categories kind of fit together, but let's just deal with these. So unmanaged just means it does not support any configuration interfaces and it doesn't support any options. Basically, if you want to use this, you plug computers into the switch. That's it. Those are found in home networks, SOHO, which is small office, home office, or just small business networks. A managed switch is going to support configuration management using various interfaces. So there'll be the console port connection, which is a direct physical connection. Some of them support connections over HTTPS, virtual interfaces through Telnet, SNMP, Simple Network Management Protocol, to gather information. Syslog would be another one potentially. So they're going to support additional management and monitoring. And they also have increased functionality using switching protocols. STP, RSTP, we'll talk about some of those, trunking, with the VLAN trunking protocol. Those are typically going to be managed switches. You can increase authentication or increase security, by requiring authentication. And then typically they have support for VLANs, and we'll be talking about VLANs a lot more. A web smart switch is a hybrid between the two. These are usually implemented in order to increase capabilities but minimize cost, because they're going to be much less cost than a full-on, layer 2, layer 3 managed switch. There are a lot of switch characteristics that are in the objectives. These are terms that we need to be able to recognize. So port mirroring is a concept of mirroring or duplicating a port. So it says duplicates all traffic on a single port to another port. And this is typically done for monitoring. Traffic monitoring, network diagnostics, something like that. Think about the switch and how it isolates traffic from one port to another. Well, that means that if I'm trying to monitor a system, I'm only going to be able to monitor the communications between myself and that system, unless you do port mirroring. And this is just a configuration that would be done on the port. By the way, just so you know, 99% of switch configuration is going to be using a CLI, a command line interface. Whether they're HP ProCurve switches, Cisco Catalyst switches, Aruba switches, fill in the blank, they're all going to have a CLI typically, and that's how I would be configuring this. In Network Plus, we don't get to that level. You may do some of those things in some of the lab exercises just to get a handle on it, but they're not asking questions to that level. We're really more dealing with, term recognition, understanding what the term is and what it actually means in terms of a scenario. That's what we're dealing with. So port mirroring duplicates the traffic from one port to another. Channel bonding or port bonding is going to increase the throughput by using multiple NICs bound to a single MAC address. Okay, and so you're basically effectively doubling the bandwidth by increasing that. And there's a protocol for this. Just recognize the acronym. Link Aggregation Control Protocol is a Cisco protocol that is used for port bonding. Power over Ethernet, PoE and PoE Plus, these are a couple of standards that are on the objective still. Basically, simply put, they pass power along with data using standard Ethernet cabling, okay? Which in this case, it provides longer cable lengths, unlike other standards, but it also provides power to remote systems without having to run electricity. So along with the data that's being transferred, you also have power. A lot of today's modern switches are going to be PoE, PoE Plus, whether or not you actually use that functionality. But in reality, you really shouldn't get a switch that's like that unless you intend to use it. If the switch can be plugged into power, then we don't need power over Ethernet. Unless we've got remote devices remote to the switch that we need to pass power to, that would be a possibility. Now let's talk about some of the virtual capabilities that we've got. Teaming is one, and that's just a kind of a generic term that stands for combining multiple network connections to be able to increase bandwidth and possibly even reliability. Link aggregation, port teaming, NIC bonding, NIC teaming, port bonding. The terms teaming and bonding are kind of used interchangeably. What it means is twofold. Number one, you have multiple network cards, but they're configured with a single virtual MAC address. So the packets that are headed to this network card will be equally distributed between two physical NICs. So you do increase the bandwidth, and you do provide yourself with fault tolerance. Should one of those physical NICs go down, you can still communicate with the system because it's got this NIC team. Now Windows servers have been able to do this since about Windows Server 2012, I believe. We also have hardware and software load balancers that would essentially do the same thing, set up a virtual network interface with a virtual MAC address, multiple IPs, and then distribute traffic that's destined to that to systems that are behind the load balancer. Not technically the same thing, but very, very similar in functionality. A virtual LAN or VLAN, an advanced filtering technique that's used by modern switches that allow computers to connect to separate network that are connected to separate network segments to appear and behave as if they are on one segment. Now, that's a bit it's a good definition. I mean, it's an accurate definition, but it can kind of be misleading because you can have a VLAN, you can have multiple VLANs on a single switch, or you can have a single VLAN across multiple switches. Okay, well, it's that second definition that really matches up with this. Computers are connected to separate segments, they're connected to separate switches, but they all appear and behave as if they're on the same segment. Okay? In a single switch where you have multiple VLANs, then you're actually trying to logically segment these systems to control traffic, much like you would with subnets on a router. You can do the same thing with VLANs on a layer 3 switch. All right, so let's talk a little bit more about the virtual LAN. One of the key advantages to a VLAN is that modifying the network does not require physical changes. Picture in your mind a 48 port switch. That means 48 wires going into the front of it from the patch panel, all eventually connected out to computers and workstations. Okay, if I was using a router and I wanted to change the IP subnets, I would have to physically modify the configuration. I would need 2 physical interfaces on the router. I would need to wire a switch into each of those interfaces and then systems into the switches. Okay, we would have to physically do it. If you're doing this with a layer 3 switch, let's say I've got 48 ports and all 48 are associated with the default VLAN. I could go in and I could say ports 1 through 24 are the default VLAN, and ports 25 through 48, those are going to be my custom VLAN. Okay, automatically the computers that are connected are now automatically in a logically separated network, but I didn't physically have to do anything with them because all I really did was go and do port-based groupings. All right, now technically there are multiple types of groupings. You can do port-based, which is based on the physical port the machine is connected to on the switch. You can do address-based groupings, so that allows IP addressing to addressing to define the VLAN, so packets are only forwarded to the appropriate VLAN. You got protocol-based groupings, which allows the switch to examine the access protocol, that's layer 3 switching, and subnet-based groupings, which allows for switches to identify the appropriate subnet and forward it accordingly. Now, that's just like a router-based subnet, although other than the fact that it is logically configured. When you first put a switch on the network, there are some configuration options for managed switches, all of which is not going to be the same for every switch model, so just keep that in mind. This is just kind of generic. The initial configuration of a switch does not include a management IP address, so you can connect to the console port, but if you want to use HTTPS or Telnet or even SNMP, we need to assign the switch an IP address. This is an IP address that's just going to be used to connect to it over the network to perform management. Okay, we should also define a default gateway along with that IP configuration. We should set the time. This helps with logging and monitoring. We want to make sure the time is not UTC, but it's actually the appropriate time zone. In a multi-switch environment, you can use neighbor discovery, either the link layer discovery protocol or the Cisco discovery protocol. Don't need to know the ins and outs of those. Just they've actually removed them from the objective. So those are protocols that just allow switches to interact with one another and communicate with one another. We could configure logging. So syslog is a very common protocol that's out there that allows network devices to send log messages to central management servers. That clearly has to be configured, as would Simple Network Management Protocol. Another monitoring type of protocol, but also has the ability to make configuration changes. SNMP has various versions. The latest version would be version 3, and it supports some security capabilities, okay? Because SNMP allows me to query a network device to obtain its configuration and potentially allows me to push a configuration. Well, we wouldn't want anybody to be able to do that. So a very simple security is setting up the community name. It's sort of like a work group of switches, a work group of network devices. So that would be part of the initial configuration if you were using SNMP. Beyond the initial configuration of the switch, we would have the configuration of interfaces. Again, in many cases, this doesn't need to be done. Small, simple environments, you just plug it in and go. But the larger, more managed environments, we may need to go in and make changes. It's going to be completely dependent on the scenario, but each of these settings is configurable at the interface level. On a switch in the command line interface, you'd get into the configuration, then you'd get into the config for that particular interface, and then you can set certain values. Okay, so for instance, if I wanted to change the speed and duplex settings, like we mentioned before when we were talking about a NIC can be full duplex, but if the switch port it's connected to is not configured for full duplex, then we're not going to get full duplex. All right, so if I've got a couple servers that I do have that set up, I'd need to go and configure that. If I want them to operate at a slower or higher speed only, it's going to auto sense by default. I'd have to configure that. VLAN IDs, VLAN tags. The VLAN tags is used, and we'll talk about this a little bit later, when you have multiple VLANs, or a VLAN, I should say, that spans multiple switches. Okay, we're going to need VLAN tagging, VLAN IDs, configured on these ports so that it identifies what VLAN they're associated with. Port bonding, if you want to aggregate the bandwidth of two ports, you'd have to configure that at the interface setting. Port mirroring, either local or remote, is going to be done at the actual interface itself. So we go into the CLI, the command line interface, and we determine what's needed, and then we get into those ports and we actually make those changes. Now, in larger, more complex network infrastructures, we need switching protocols. These are used to ensure the efficient handling of network traffic as well as to provide isolation. The most common one was Spanning Tree Protocol, STP. And this primary goal here for STP is to ensure a loop-free topology on switched Ethernet networks. So it prevents loops and it prevents the broadcast radiation that results from them. This essentially allows, simply put, it allows switches to talk to one another, to be able to identify the multiple paths and specifically redundant paths within the network so that they're not broadcasting packets, where it's not needed or where it would cause a loop. It's standardized as IEEE 802.1d. There's a more recent variation known as Rapid STP, RSTP, 802.1w. Both of these create a spanning tree of links to a root switch to ensure that links that are not part of that spanning tree are disabled. Basically, make sure there's only one active network connection between any two network nodes, because if you have multiple connections between two nodes, then that's what's potentially going to duplicate packets and cause loops. The STP protocol specification states certain states, for lack of a better term, states of a port. Okay, so again, if you really take this further and get into how to construct switches and lay out a network and whatnot, you probably have to get a little bit more information on STP. But STP largely is self-sustaining. Basically it's just enabled on port or on switches. And managed switches, it would be by default, and they really just are communicating with one another and make these determinations themselves. Okay, they define a single root switch, as we said, and then they make sure that they only have one path to that root switch. So during that discovery process, ports can have multiple states. If they're in a blocking, state initially, they're not going to forward any traffic on that. They then go to listening and to learning as they determine their path to that root switch. If a path is seen as in the active path to a root switch, if a port is seen as in that active path, then that port will switch to forwarding. That means it is forwarding packets on that port. If it is not a part of that route to the active switch, then it'll be put into the disabled state. All right, so those are the 5 states. The state of the port is determined initially when a device is connected into the port using information gathering frames, which are known as BPDUs, Bridge Protocol Data Units. That's just the way that these switches are communicating with one another. RSTP switch ports can have different states, discarding, learning, and forwarding. So discarding is basically like blocked. I'm not going to pass packets that would represent a duplicate path. Learning, I'm still trying to figure it out. And forwarding, this is good. This is fine to forward. It also adds additional Bridgeport roles in order to speed up convergence in the case of network failure. So you have a root, a designated root switch, alternates, backups, disabled. Again, all of those are automatically determined by the switches themselves. There's one root. There is a designated path to that root. There's an alternate path to the root, or you have disabled. All right, let's move into trunking. Trunking provides the ability for multiple VLANs to utilize a single connection, and it's made simpler with trunking protocols like the VLAN trunking protocol, or VTP. Without VTP, you'd have to configure trunking on each individual switch. With VTP, the configuration is greatly simplified. Now here we see a single router, that's the circle. The squares are switches, and we have two VLANs. But notice that VLAN 1 and VLAN 2 traffic will be utilizing the same path out through the router. That's why you see the double lines there, okay? So VLAN trunking provides that capability, transferring packets for multiple VLANs across a single segment. Trunking protocols are also used with network switches in conjunction with the use of VLANs. Standardized as VTP, the VLAN trunking protocol, or IEEE 802.1q. You definitely want to recognize that standard name. Carries multiple VLANs through a single link, referred to as the trunk line and the trunk port. The way it does this is by adding VLAN tags to the Ethernet frames in order to identify the VLAN across multiple switches. There's a Cisco proprietary tagging protocol called ISL, and then 802.1q, or VTP, is the non-proprietary tagging protocol. When there's only a single VLAN, there's no need for a trunking protocol. This usually is referred to as the native or default VLAN, and frames would be untagged. But in the graphic below, you see when there are multiple VLANs, there's an additional 802.1q header that is going to provide the VLAN tags, and that is simply to identify the VLAN that a particular packet is associated with. All right, so talk about some additional management for switches. You know, the complexity rises when we're dealing with enterprise networks. So one thing definitely is going in and creating additional VLANs. Okay, so larger environments or environments where we want to control traffic, we may have 5, 6, or more VLANs. We should always be changing usernames and passwords from the defaults, just like any other network device. Default passwords and usernames are very easy to find on the internet. And so that's one of the first things we should do is get in and modify those. Enabling AAA, authentication, authorization, and accounting, that gives us higher security. When we do that, we're talking about actually implementing a standard called 802.1x, which utilizes the Radius protocol. This means that a client that's connected to a switch port has to authenticate themselves to another central entity. That could be a Radius server, that could be Active Directory in conjunction with a Radius server, but in any case, you are providing that additional authentication. We can even actually require multi-factor authentication by setting up AAA. Enabling, disabling console port access. So the console port's on the back of the switch. If you don't want anybody who has physical access to the switch to be able to log in that way, then we can turn it off. We definitely, have those VTY, virtual terminal ports, and we can configure access to those and passwords as well. Okay, so access to them, enabling AAA on them, those kinds of things. You're controlling the way in which you can manage the switch. All right, so we just finished our topic on switches. Again, not a lot of demos to show you, but in the Network Plus, they're not going to get to that level. We need to understand functionality. We need to understand acronyms. We need to know how and where it's used. So I'm going to pull up the objectives here just to make sure that we got all of this. You're going to find this. Let's see, where are we going to find this stuff? Number 2, domain number 2. Okay, we have the initial network implementation. So we've kind of talked about some of these. There are a few others that we'll hit later. So we're going to get all of 2.1 here as a part of this chapter. 2.2 is routers. 2.3 is switches. Now I will say, I mean, this has been simplified from what it was previously. Okay, so I actually had some stuff in the chapter. I got to go scan down here just to make sure. Yeah, I had some stuff in the chapter that I still just think is useful information, but that they're probably not going to ask about. Okay, so we've got VLANs. I don't know that I distinguish between data and voice VLANs, but that would just be one type of VLAN for us to do. Okay, voice carries voice, data carries data. Port configurations, though, we did mention port tagging, 802.1q. You see that's mentioned, the VLAN trunking protocol. And then port aggregation and the link aggregation control protocol. Duplex is half or full. Speed, the speed of the port. I did not mention flow control. Sorry, that is just an error checking mechanism. That's another port configuration that you can do. We talked about port mirroring, port security. These last ones we didn't but I'm actually we'll talk about those a little bit later with storage area networks. Jumbo frames, carrying data. Sometimes you have to increase the MTU, the maximum transmission unit, on that. Okay, and so that's, again, it would be a port configuration. The auto medium dependent interface crossover, MDIX, is basically just the elimination of the need for crossover cables. It's an auto sensing capability that typically is going to be on every port by default. We talked about media access control, or MAC address tables. I guess I didn't go into this in great detail, but I did mention the term. MAC address tables are developed and built by the switch. Remember, we said the switch has the ability to forward traffic based on who it's going to, and not forward it if it's not headed to a destination system. Well, that's done by the MAC address table. So the switch initially learns all of this. It learns by examining frames which MAC addresses are connected to which ports. It builds that table, and then it uses that table to selectively forward. Power over Ethernet Plus, we talked about. Spanning tree protocol, we went into RSTP. Again, you don't need to necessarily worry about the states of the ports and whatnot, just understanding the functionality. The functionality it provides is to ensure loop-free communication. CSMACD is the access method for Ethernet. We've talked about that. Neighbor discovery protocol and or ARP are both ways in which switches can discover other systems between them. ARP is the way, of course, that we resolve MAC addresses, IP addresses to MAC addresses. The neighbor discovery protocol is exactly the way that it sounds. So that's really all we've got on switches. As I said, they've scaled that back from version 007, so there may be a little bit of information in the chapter that you actually didn't need, but it can be useful just from trying to comprehend this and understand it on a daily basis. So now that we've discussed network switching, we're going to move up one layer in the OSI reference model, as well as TCP/IP's model, into the network or internet layer, depending on which one of those you're looking at. This is where the routing of packets based on protocol addresses is utilized as a means for forwarding traffic. So a layer 3 device is primarily dealing with two things: the addressing of packets with protocol addresses, and then the routing of those packets based on the protocol addresses. So every packet has an source IP address, destination IP address, and those are the actual values, specifically the destination IP address, that is used to route the packet from one network segment to another across a series of routers. So routing then is simply the process of selectively forwarding traffic from one network to another. Now we do have hardware versus software routing. Hardware routing means we have a dedicated actual physical router. Most of us, that's going to be the case. Even small office, home office type of networks, we're typically all now connected through a router slash wireless access point that gets me physical connectivity out to the internet, right? That's probably connected to a cable modem, DSL modem of some sort. So that still is hardware routing. Okay, that's not considered software routing. Software routing is like within an operating system. The Windows server operating system would have this routing and remote access service. It was one of the things that was probably almost never used in a production environment because it suffers in terms of performance. I used it in test environments. We could use it to kind of duplicate a production environment, to demo it or test, functionality of some application, things like that. But from a performance standpoint, you generally don't see it. So hardware, there are dedicated routers. Those dedicated routers use layer 3 addressing or IP addressing to determine the route that a packet should take. Now, you might be wondering, well, if all layer 3 addresses, network layer addresses, are IP addresses, then why do we just not call them IP addresses? Well, because if we go back 25 years, it wasn't always IP. It was IPX and IP. IPX was in Novell's IPX SPX protocol suite, which was a competitor with TCP/IP in a sense, used for Novell networks. You had some even older than that network infrastructures that would have their own protocol suites. Okay, so that's why it wasn't always the same. Today, it is. Everybody uses TCP/IP as the networking protocol stack. And so everybody's using IP addresses, and we could now use them as synonyms. All right, so those IP addresses are stamped on that packet that's coming down the OSI reference model, and we need to get it to the destination. So we stamp an IP address for the destination computer and an IP address of myself as the source onto that packet. The very next thing that happens is a routing table is examined. And I'm talking on the computer that's sending the packet. The routing table is examined because it's looking to say, hey, that destination IP, is it on my network segment or is it on a different network segment? We talked about this with IP addresses. If it's on my network segment, then I'll go ahead and process the packet, and I'm going to end up sending directly to that computer or server that's on the same subnet. I don't need a router. Okay. However, if during that determination it's determined that the network, the device I'm trying to communicate with is in a different network segment, well, then at that point the routing table is going to direct me to send the message to the packet to my router. All right. When we think routing tables, we typically only think routers, but actually every client has a routing table as well, and I'll show you that in a demo, just so you kind of see how it functions. So it does exist on the client. It definitely exists on the actual routers themselves, and it works in the exact same way. I mean, either the routing table has an entry for the network ID of the destination packet, or it doesn't. I mean, that's essentially, it either does or it doesn't. If it does not, then every router has its own default route or default gateway that it's going to use. Now, true traditional, hardware routers, their routing tables might contain entries for networks that they are not directly connected to. That would be a difference between it and a client computer. But those routing tables would have to be updated in some way for that to happen. A router, just like a computer, only knows by default about the network segments that it's physically connected to. So if we had a series of 5 or 6 routers, creating a WAN or a larger enterprise LAN, then I need to know about the networks that exist in the other areas. So the routing tables have to be updated, because otherwise everything just goes to the default gateway. And that update can happen manually. It's called static routing, or dynamically using routing protocols. And this is going to be sort of the biggest gist of what is actually on the exam, what they're expecting you to know. Now, the type of router that's used is going to be varied based on the organization's requirements, connection type, size, things like that. But a router's job remains the same: route packets from one network segment to another. All right, so here's a look at the routing tables. These are used by clients, servers, and routers in the same way in order to determine exactly where we want to forward those network packets. So basically, it's looking at the table and it's determining whether a host route exists in the routing table. Okay, in other words, is there a route for this particular IP address? The answer to that is usually no, but it still checks. Then it looks at the destination IP and determines whether that destination is local or remote. That's through the process of ANDing with the subnet mask to basically figure out what is the network ID. Once a router, once it figures out the network ID, is then going to look at its routing table for an entry that's matching that of the destination host. If it finds one, it will forward it either directly to the host in the case of a direct connection, or it'll route it in the way that it's supposed to route it, okay, which could be through another router. And then finally, there's the default route. Okay, so I mean, that's the three things. It's, do I have a record in my routing table of that computer specifically? Usually no. Do I have a record in my routing table of that network specifically? Yes, if it's local, and yes, if I've got routing table entries that came from other routers or were put in manually. Okay, and in that case, it's going to define where it's supposed to go. If I don't have any entry, then I just go to the default route. And so that's, again, that's what the computer does. That's what routers do. They just happen to be attached to multiple network segments by default, and also capable of using routing protocols to actually communicate with other neighboring routers. In this demonstration, we're going to take a look at the routing table that you would see, and we'll just use a Windows machine just because it's a little bit difficult for me to access another routing table in a demo fashion, but they're going to look the same. So it really doesn't matter if you're looking on a Cisco router or HP router or whatever. It's going to look very, very similar, and so the concepts can be seen. In Windows, this is route print. In a Cisco CLI, it's show IP route. In PowerShell, it is get, let's see, what is it? I think get net route. Yeah. Okay, so get net route in PowerShell, route print in command line, and then show IP route in the Cisco command line. I'm going to go back to the route print, although they're all relatively the same. They just kind of lay it out a little bit differently. Let's maximize this. Go up. Oop. Okay, so here we have the routing table, and there's a couple of important things here. First off, our columns. Network destination is going to be the network that it's headed to. Net mask is going to be the subnet mask. The gateway is the IP address that it will be going to. And then the interface is the address that it's coming from. Okay. Now, in this case, all zeros in both the destination and the net mask, that represents that's the default route. And it used to say default route down here somewhere. Maybe it was up at the top. Let's check and make sure they don't still do it. Yeah, they're not doing it anymore in this one. So it doesn't actually say default route. It's just got the all zeros route. Okay, but that's my IP address. So that interface is my IP address, and it's just essentially saying if you want to get to a network that you don't know about, then send to 172.20.0.1, which is my default gateway. What gets confusing sometimes in here is that we've got a lot going on that we don't necessarily expect to see. So 127, so let's do this one first. 127.0.0.0 with a net mask just saying match is the first. So if you use 127, it's going to the loopback. Well, why do we have this? Well, look at the difference between these two routes. This one's a full IP address, and the mask is a full 32 bits. Now, that's not legitimate if you're like assigning somebody an IP address, you would never do it that way. But in access control list and packet filters and routing tables, when you want to do a direct match on a remote address, you put the address /32, or in this case, followed up with a bunch of 255. On link also means it's directly connected. So what you'll actually see is that for each network, you're going to have 3 entries. The network itself, your IP address on the network, and then the network broadcast address. Okay. So here, same thing, 168. Well, this is actually, I'm not really sure where that one's from. That might be my public IP. This is a machine in Azure, a VM. This is just the 169.254 automatic private IP address. And then we've got the network that I'm connected to with the 32-bit or with a 24-bit subnet mask, but notice it's saying on link again, so I'm going to just connect to it out of this interface. And we have my specific address on that network, and then we have the broadcast address on that network. And we got some multicast stuff, and then we have some all subnets directed broadcast. So, as I said, the computer itself, really only knows, a client computer is only going to know about the networks that it is directly connected to. Now, I could add a route and tell it how to get to another network, but unless I have two network interface cards, then that's really not going to be that important. Let's test and see if this is true here. If true, if I do a trace route -D and I ping another machine on the same subnet, if I try to ping another machine on the same subnet, it should come right back. Oh, great, of course. I forget the firewall's on that other machine. So it's going to block me, and I'm not sure. All right, let's get that particular problem fixed. All right, we're actually not going to be able to fix that because that virtual machine is not even running. So anyway, I was just going to show you, and I can just do the same thing with 0.1 here. I had a couple VMs running, but you'll see there it's going to trace the route, and it's going to do it very quickly. Screen is too big here. Or sometimes maybe this isn't going to work either. That does looking like trace routes using ICMP. So sometimes ICMP doesn't work. I'm only using trace route instead of ping because I was just trying to see the path that it was going to take. But I forget that struggles in the Azure cloud because they block it. So I can certainly ping 172.20.0.1, and I should get a response back from that. But even that, see, it's not the router. My default gateway is not responding to ping, which is somewhat abnormal. All right. Point of this is really just to see the usefulness of the routing table and to look and see how, basically your computer, when it identifies the packet or the IP address of a remote destination, all it's doing is looking and comparing it against this routing table. If it finds a match, it'll send to the gateway on that entry out of or from the interface. So that's the meaning of those two. Gateway where it's going to, interface where it's coming from. On a router, the only difference is you would see a couple of additional networks because the router's connected to multiple networks. So we put in layer 3 devices for multiple reasons. One of them is to actually create segmentation. The segmentation that is provided by layer 3 is in the form of an actual subnet. Now these could be physically separated from one another in the case of physical routers. They can be, kind of logically separated from one another in the case of a layer 3 switch. So layer 3 switches have the ability to do subnetting, but it's all in VLANs. It's all logical. But that's where we have a mixture of layer 2 functionality and layer 3 functionality sometimes. Right? Let's just deal with the layer 3 for right now, but I wanted to mention that. So benefits of segmentation, well, certainly to separate public and private networks. So you see this often today. You'll have Wi-Fi networks that are set, a particular company's guest Wi-Fi and then their actual business Wi-Fi. Wi-Fi is kept segmented from the rest of the LAN in many cases. Routers may have packet filters that control traffic between a screened subnet and a private LAN. So that's one benefit. Another benefit is optimizing performance because a layer 3 device is the only device that is going to actually create separate broadcast domains, plus provide you with packet filtering capabilities, which is limited firewall capabilities to control traffic to and from particular subnets. Implement security controls. That's in the form of packet filters. Load balancing, high availability. That's another reason to segment the network. You're not everything is on one single network infrastructure. Create test networks, create honeypots for security checks, fulfill compliance obligations. These are all different reasons why we might segment a network with routers or layer 3 switches. All right, hardware routers are dedicated devices. This is an image of a hardware router. It's got the inclusion of a CPU, memory, storage. They're actually very specialized mini computers. They have multiple physical interfaces. What you actually see would depend on the age of the router. Also, you can't necessarily tell from the graphic, but anytime you see those groupings of 4 ports, and definitely the ones with the little 1 port, the quad form pluggables over on the left for fiber, those are removable interfaces. Okay, much like a PCI card could plug into a computer, those will plug in flatwise into the back of a router. They call them modules, so you can reuse, you can utilize new media, things like that. Obviously, some of the things in the list, token ring, FDDI, you're not going to be seeing those. You're not going to see them on the test. They're just kind of old, antiquated technologies. Ethernet, definitely. RS-232 is technically that's a serial port. Okay, V.35 would be for an analog modem. Probably not going to see that. Some sort of broadband capability, cable, DSL, in the past, T1, T3, that kind of stuff. Connectivity out to the ISP. Hey, today, most of us, our home routers especially, we've just got Ethernet. That's it. We've got an Ethernet cable that plugs into a cable modem, and we've got an Ethernet and the same or a different Ethernet cable that plugs into the router. That's it. It just has a special WAN interface. Business-style routers are more likely to have high-speed connectivity options. Software routing is handled by the network operating system, and that's going to be used, as we said before, in much smaller situations. All right, so routers only know what they know, and they, like a computer, only know about the networks to which they are directly connected. The only way to tell them about other networks is to either manually add it and create a static router, or to go with dynamic routing protocols. Okay, so this is looks like a Cisco router based on the command line or the command show IP route. So it's showing the routing table on a Cisco router, and it shows the destination network, the subnet mask, and the gateway and the port that would be used. Now these look like they're all this looks all the same. It has all the same gateway as if it's connected directly. So not a great not a great example, but just a graphic. We already looked at the routing table on a computer, so we've discussed this is how it's out there. But how do you get stuff in there? Well, you can either manually add the route or you can use dynamic routing protocols. Now, when we use the term routing protocol, it might be easy to get confused. We're not talking about protocols that are used to route packets. That's IP in TCP/IP. That's IP's job. Okay, so routing protocols aren't to route traffic, but instead they're to distribute route information among routers so that they can route the traffic more efficiently and correctly. Again, you have to be in a situation where you have multiple routers. So you have a router that is only connected to a couple of network segments, and yet there are more network segments that it would have no knowledge of. In those instances, we have to, for instance, in the graphic, tell router C, hey, in order to get to that network that's between router A and B, here's what you do. Because see, router C wouldn't know about that network by default. It would only know about the network connecting it to A and it to B. It would not know anything about the network connecting A and B. Simple graphic, and this graphic is talking about more, different kinds of protocols and whatnot, but simple graphic explaining this is why I need this. Now, the routing protocol that gets chosen is going to be based on the physical router type. So some routers will only support proprietary protocols. The size of the organization, the number of routers, the location of the router within an autonomous system, which just kind of a synonym for a network, an organization's network. Is it inside that or outside that in terms of ISP? The routing protocol might be chosen based on high availability, performance requirements like latency. How long does it take for updates to get passed? When there's been a change to network status. Convergence, how long does it take for an updated route to get to all the router? Okay, so they're going to vary based on that. And really here, we need to be able to identify, these protocols by acronym. We just need to identify whether they're internal, external, or interior, exterior, based on the type of routing protocol, how it would make decisions. We are really still talking pretty high level at this time. So dynamic routing is just, hey, I'm a router, you're a router, let's talk. You're connected to those networks, I'm connected to these networks. Let's share the information that's not common to both of us, right? I mean, that's essentially what it's doing. And then if there's any changes, then let's communicate then too, so that we aren't routing packets down a path that's, ultimately they're going to be dropped. They fall into three distinct categories. They are distance vector, link state, and path vector. The different protocols will treat updates differently, how to evaluate paths differently, etc. Before we get into those, let's talk about a metric. What is a metric? Well, there are multiple router metrics, but a router metric in general is just the way that the router will decide one route over another. If it's got a packet and there's more than one path that it could take, how is it going to decide? A real simple way is hop counts. Right? If it takes me 2 routers to get to you from this way and 5 to get to you from another way, I'm going to choose the 2. That's simplistic. That has its problems, or has had its problems. And so they've kind of worked in mechanisms to fix how it operates. But that's a simple and easy to understand mechanism. Depending on the routing protocol, you might have other things like the maximum transmission unit if you need a path that supports larger packets. The bandwidth that's available, Okay, so I can get to you with 2 hops over here using a 100 megabit per second connection. 2 hops over here, but it involves an analog modem and a real old style connection to get there. But my 5 hops is all over high speed networking. Well, my 5 hops is probably going to be better, right? It evaluates the bandwidth. Cost, which are administrative, like a cost that can be associated with a path. Latency, the time it takes for an update to get pushed out. Administrative distance is an actual value that I would configure so I can control the routing. And then there's an IEEE standard. You actually don't, they've dropped this one. You don't need to necessarily know it, but 802.1AQ, shortest path bridging, was just an automated way for this to be done, specifically with layer 3 switches. All right, so let's go look at those types, distance vector versus link state. Distance vector is pretty simple. Each router connected to the network basically just passes a copy of its routing table to its neighboring routers. Okay, so I'm like, okay, I know about networks A, B, and C. I'm just going to shoot you my routing table. That machine shoots back and says, well, I knew about network C, but I don't know about A and B. However, I know about D and E. You know what I'm saying? So we're just exchanging routing tables. We're looking for routes that we didn't know about, and then using the information from that routing table update, along with metrics, I'll determine the distance of a particular route. Okay? In real simple form, it would just be, okay, well, you told me you were directly connected, so I'm going to put it on mine with a hop of 1. Hop count of 1, right? They always use distance vector, will always use the route with the fewest number of hops. A link state routing protocol is more complex. It floods the network with information in an attempt to build a database of routes and other segments. The routers then exchange information like speed, route quality, availability, etc. They build a map. This map is basically maintained on 1 or 2 systems for high availability. And it acts as a database or a diagram, I should say, of the network. So anytime there's a change, then the individual router detecting that change will notify that central station, and the central station will then produce a new map and shoot out the updates. Okay, so convergence, the amount of time for it to take an update from a reporting router to all other routers, convergence is going to be very small in link state. It is far more. These are far more complex routing protocols capable of making quicker and better decisions. A path vector is different. Both link state and distance vector are intra-domain protocols, so they don't scale well. They can't be used outside an autonomous system. That means they can only be used inside your LAN, essentially, inside your LAN. So path vector uses an inter-domain routing where the router keeps track of the path for a packet from source to destination. It also identifies each autonomous system as a node along the path, and the packets flow until they reach the autonomous system of the destination device, at which point they would be passed into interior routers. These would be for large, complex internetworks. Again, depending on where you go with this certification, you may never actually work with these. I've been teaching and talking about these conceptually for years and years and years. And I've set up both the link state and the distance vector protocols in working environments as well as non-production environments. Personally, I haven't dealt with a path vector protocol. So that's my only point. Just kind of depends on where you end up taking this knowledge, but the test wants us to know the difference between the three. Most of us would be dealing, if at all, with interior routing protocols. Interior routing protocols are inside an autonomous system. Okay, that's just within the organization's network. RIP, Routing Information Protocol, is based on a distance vector algorithm. It normally uses the fewest hops to reach its destination. Now, the original version of RIP was classful, and it didn't support variable length subnet masks, so RIP v2, which would be the current version, has enhancements that provide classless IP support, VLSM, variable length subnet mask, enhancements to security in the form of how the updates happen, reduce broadcast traffic by using multicast. RIP would be broadcast, basically, hey, here's my routing table, and it wasn't very configurable and it wasn't very secure. So RIP v2, though, can be used today. It's often RIP v2 or OSPF, Open Shortest Path First. Now, that is a link state protocol that provides for the configuration of hierarchical topologies and helps quick response to changing network conditions. Another way of saying what we just did, basically. Builds an initial map. When there's a change, the router reports back to a central monitoring station. That monitoring station produces a new link state database and then pushes out the delta updates. IGRP and EIGRP. IGRP was a proprietary Cisco protocol that was created to overcome some of RIP's shortcomings. EIGRP was the second version of the Cisco proprietary protocol that addresses the limitations of IGRP, like adding support for classless and adding support for quality of service and adding support for security, etc. Okay, but those are some of the basic routing protocols you can run into. Exterior routing protocols outside an autonomous system used to exchange routing and reachability information between ASs connected to the internet. A border gateway protocol is an exterior routing protocol. It's a hybrid that bases its decisions on paths, policies, or rule sets that are configured by administrators. Is no longer on the exam, but it's just I left it on there just to have a second example of an exterior gateway routing protocol designed obviously between autonomous systems. All right, uses advanced metrics and features very high speed convergence. Okay, so very large enterprise networks working for service providers of any kind. That's where we would start to see these exterior routing protocols being used. Now, we've already defined convergence. I don't know that it's necessarily a routing problem. The other two are, but long convergence would be a problem. Convergence is simply the amount of time that it takes for a change in the routing table or the database to be distributed to all routers and then packets redirected. Without accurate and efficient convergence, you could have routing loops. Routing loop is simply a process in which two routers discover different routes to the same location that include one another. And that's a bad thing, right? If you think that you're getting to network A through me and I think I'm getting to network A through you, then we're just going to have a packet that's bouncing back and forth until the TTL, the time to live of the packet, expires, and at that point the next router that gets that packet would just simply drop it. Okay, but it causes a bunch of excessive traffic, and so it is a problem. Most of your routing protocols now in the last 10, 15 years have had built-in automatic mechanisms to prevent routing loops. The count to infinity is when a router goes down, but the others don't realize it and they're broadcasting incorrect information. So it causes the recalculation of hop counts until the infinite hop count is reached, which is, again, 16, depending on the routing protocol, that determines the infinite link. Okay, so count to infinity and routing loops are very much related to one another. And the other thing I should say is they are pretty much solved as well through the use of modern routing protocols. All right, in this next topic, we're going to be looking at some other network devices. These aren't considered the core devices, routers, switches, hubs, etc. But there are a lot of network devices, and all that means is a device that's connected and can communicate on the network. Okay, and so we're going to go through a variance. It's just coming off the objectives, a list of devices that we need to understand the functionality of and purpose of. We'll start with the term gateway. Now, we have thus far used the term gateway to describe a default gateway. That's my router, my way off my local network segment. But that term can be used in a broader sense as well. Okay, now they won't say default. If it just simply says gateway, we need to look at the question to try to determine exactly what they're referring to, because a traditional gateway is any device, whether it's software, physical system, that does some sort of translation between incompatible systems. The only one actually mentioned on the objectives is a voice gateway. A voice gateway is used to translate between private branch exchange, the old PBX style phone systems that businesses used, and voice over IP systems. Okay. Another example, and this goes back in the early days of like Exchange 2007-ish, where they brought in unified messaging for email, and all that meant was that voicemails got delivered to the email system. Now, that's a very common thing in today's businesses, but it requires some sort of gateway, some sort of translation between operating systems, between network architectures, between email formats. That's a gateway. Switches, you get a couple terms that get used here. Multi-layer really is just a kind of a generic term for devices that do both routing and switching. Okay, so they can be called layer 2 router. Layer 3 switch is probably the most common. IP switch, possibly. They can also be used for quality of service, and in doing so, they'll use a portion of the packet header called the Differentiated Services Code Point, or DSCP, and that is used to identify the type of traffic. And the idea behind quality of service is that we can establish base levels of connectivity, of bandwidth that are required for particular types of network traffic, and then enforce it. Like video, like audio, that's going to require higher speed transportation than regular data packets would. So that's quality of service. And then content switches are higher layer switches, like up at the application layer. So they're not doing layer 2 switching at all. It's switching inbound connections to a group of servers or to groups of firewalls. They can do their switching based on groups of remote IPs, particular applications, a specific URL. Okay, so it is a high-level type of load balancer, allowing us to stand up multiple systems doing the same thing behind the multi-layer or behind the content switch, but filter at the application layer. One of the common things we see in today's networks is the use of voice over IP, basically using IP technology that already exists that connects all of our systems to transmit calls. Now that requires, specialized protocols, it requires specific network devices, but it's becoming very, very common. In fact, many people are even using voice over IP at home. Now, true voice over IP phone is one that does not connect into a phone line, but instead connects in with an RJ45 connector into a standard Ethernet line. These phones are typically split off from the rest of the network into voice VLANs. But other than that, I mean, they're communicating just over the network. Basically, each one gets an IP address on the network, but then also gets something known as a SIP endpoint. SIP is Session Initiation Protocol. We mentioned that earlier with the ports and protocols, but that's the one that establishes sessions for the transportation of voice over IP data. And then Real-Time Transfer Protocol, RTP, actually transfers. So a SIP endpoint is all that is required. You have a desk phone that looks like that would be a SIP endpoint. You have soft phones like we see on the computer, or even a cell phone device that you can use as SIP endpoints. Okay, so all of that is possible with voice over IP. Now, when we were talking about content switches, I had kind of wished that my slides were reordered here, because the load balancer is right after a content switch. The difference, the purpose of these is the same. We stick something in front of a group of servers that are all doing the same thing. Okay, so in this case, they're all web servers. And a load balancer is a hardware device that's designed to split the particular network load across those servers. The benefit, of course, is that it increases the capacity of the system, because you have more than one computer that can be facilitating these requests. So that improves performance, but it also improves fault tolerance, because if the load balancer detects that one of these servers is not up and running, then it won't forward packets to it. That's typically done through the form of a heartbeat. Basically just a little signal that each node would send to the load balancer every 5 seconds, 10, maybe 15, something like that. It tells the load balancer, hey, I'm still alive. And so that it both increases performance and fault tolerance. Now, there technically are hardware and software load balancers. There are cloud-based virtual load balancers. Load balancers are typically for web protocols like HTTP, HTTPS, but can also be used for DNS, can also be used for email, like SMTP and other things. So the real difference between a load balancer and a content switch is how they distinguish traffic. Load balancers will always distinguish traffic based on the sockets. Okay, it'll have a virtual IP address and a port number. And for that particular socket combination, it knows to distribute the load to this group of back-end servers. Whereas a content switch, do the same thing, distribute the load, but it's going to be based on higher layer, application layer data, specific URLs, specific names, a group of servers that created a particular application, things like that. Okay, so same functionality, really same purpose, slight difference in how it's implemented. Then we have the traffic shaper. This is another device that's used for quality of service. It's used to control bandwidth in relation to particular protocols and services that helps to ensure quality of service for critical systems while still allowing others to connect, but just not giving them quite the amount of bandwidth. Now for the exam, they're just basically throwing out terms, traffic shaper, quality of service, so that you just need to understand the functionality that's provided here. Ensure that critical systems have the bandwidth that they need. And we do that by differentiating between different packets using packet headers and those DSCP points. Here we have another two very similar systems, intrusion detection system and intrusion prevention system. Now technically all IPS are an IDS as well. So what's the difference here? These are systems that scan either an individual host, in the case of a host-based, or an entire network, which would be more common. They scan it for abnormalities. They scan it for abnormal amounts of traffic, abnormal types of traffic, the addition of foreign IP addresses that are now all of a sudden sending all of this data regardless of the type of traffic, those kinds of things. Okay, and when they detect that, they will act on it. Okay, now what they do in that action determines whether they're an intrusion detection system or intrusion prevention. Intrusion detection systems, the only action that they're going to support is some form of notification. Usually via email. It's possible that there would be some sort of alarm or text message. It really depends on the IDS that you have. Okay, it's not stopping anything. It's just helping us to detect it and then notifying us. Whereas intrusion prevention systems, they'll take a step further. They'll probably still notify people, but they can be configured to take automatic steps like shutting down the flow of traffic from a particular source IP or preventing a specific protocol from being able to access this server, those kinds of things. Okay, same purpose, slightly different functionality between these two different systems. Now, you've probably all heard of a firewall. There are lots of different kinds of firewalls, and we'll go into them in a bit more detail in the security section. But they mentioned firewall here as a common network device, which of course it is. The vast majority of networking, or the vast majority of networks, will at the very least have a perimeter firewall, but most will have perimeter firewalls and firewalls that are on individual hosts, clients and servers. The Windows operating system, for instance, has shipped with the built-in Windows firewall since Windows XP. A lot of IT administrators will like to downgrade it and act like it's not useful. And I'm not saying it's the end-all be-all firewall, believe me, but it is a useful thing to have because it does provide protection. And it's protection that's enabled by default. So especially for small office, home users, it's great to have that. Most of us, though, will still have that perimeter firewall. When we get into the perimeter firewalls, we're typically dealing with hardware firewalls, and most of them are going to be stateful. Stateless is a very simplistic firewall that is only capable of filtering based on source and destination IP addresses and port numbers. It cannot recognize sessions from clients that were previously connected and things like that. A stateful firewall will be more session-oriented, more application-oriented, and be able to recognize that. And then there's different variants. You don't necessarily need to know these, but web application firewall is typically a firewall that is software-based, that is for a particular application, protecting a particular application. That's pretty much synonymous with the concept of a reverse proxy. Next generation firewalls are the latest and greatest, okay? So they have advanced capabilities, advanced monitoring, advanced diagnostics, advanced filtering capabilities, but you'd have to dig in to the individual vendor to figure out what those are. It's not like a list of specific things that they can do. And then UTM, Unified Threat Management, when we use that term, we're usually talking about combining firewall and AV and anti-spam, all right, into a single box. Could possibly also include proxy service capabilities, which is content filtering going out to the web. So the ability to say, okay, well, you can do this, but you can't go to sports sites, you can't go to social media sites during the day, except during lunch, right? So they've got extra capabilities. The general purpose of a firewall, I guess I should have said this at the start, is to prevent or to control traffic from one network segment to another. In this demonstration, we're going to take a look at a couple different kind of firewalls, just a real broad overview, just to show you a couple of the interfaces that you can expect to see. We'll start with the Windows firewall, so I'm just going to open up Control. It's kind of the old way of doing it, but it seems to be the quickest way, especially when they start moving stuff around. So Windows Defender Firewall is built into the Windows operating system. It is available for Windows 10, Windows 11, earlier versions of Windows as well. There's some basic settings here, but I'm just going to go right into advanced because that's going to look a little bit closer to what we might see on an actual firewall. Okay, now note I've turned it off, but that can just as easily be turned back on. I needed some network connectivity for something else yesterday on this VM. So the profile is on by default and should remain on unless you have problems. Even if you have problems, you should probably just create rules to allow certain types of traffic inbound as opposed to turning off the firewall. I know this is something that's debated by network administrators and has been for 20, 30 years. Many just detest the Windows firewall, I can tell you that from personal experience, and refuse to have it on and turn it off via GPO and whatnot. Not the greatest idea, but I do understand the frustration of not being able to get to a system because its firewall is turned on. Personally, I just got familiarized with the PowerShell mechanisms because remote PowerShell is turned on typically automatically for later clients, so I could remote in and I could very quickly build a rule or two that would allow me to remotely manage at very least a firewall. So, I'm kind of that mindset. Leave it on, manage it properly, add rules regardless. That's kind of a little rabbit trail. If you want to allow traffic into this system when the firewall's on, you have to create a new inbound rule. You can base that rule on program or port number, or you can use one of the predefined rules. Now, if it's program, it's actually easier just to do it out on the main page and just click allow a program through the firewall. It's just going to direct you to browse and find that program. Once you do, then it's going to create a rule that will allow that. If you want a port rule, you should come in here. Then you could specify TCP and UDP ports. You typically aren't going to do the all local ports. We typically do something like 3389 or 80 or 443, or if it's a custom application, whatever port it requires. Then allow the connection or block the connection. Allow if it secures using IPsec, and we can talk about that later. We'll give it a name. We tell it which profile to operate under. I'm just going to cancel. In the Windows firewall, there are 3 profiles. It's based on the domain membership. Users either member of the domain or is a member of the domain and has the domain profile active when they're on that network, or any other network has been established as public or private when the user first connected. You've got outbound rules too on this, and this is what you would call a host-based firewall. Okay, so let's go to this. And 20. I've got a couple of other firewalls that we can connect to. Here's actually a good example of the ports. In fact, I might have shown that before. I can't remember in a previous demo, but there, if I connect to that without the port number, it's just going to spin and spin, and then it will finally error out. Okay, however, if I put the port number in there, it will connect right away. So I'm going to go ahead and stop it because it's just going to fail. Put the port number, I immediately get a certificate warning, which is fine because it's not a trusted name or anything. And then we've got a firewall, and this is a Cisco FortiGate firewall. So give me a second. If I got that right the first time, firmware upgrade. Okay. And we're not going to look around a whole lot, I just want to see this would be another examples. We've got a VPN capabilities. We've got network interface capabilities. You go to the individual interfaces, you see the IP addresses. We can click on policies and objects, and we go to firewall policy, and we can create rules. Okay, so we got site VPNs here. We've got internals to external ports. This is actually a firewall that is a virtual firewall that is operating in the cloud. Okay, and they're all over. So this happens to be FortiGate, but in Azure I can put up other types of firewalls as well. Meraki firewalls, ASA, those are all common firewalls from Cisco. Again, this is simply meant to just show you a couple different types. So this is a virtual firewall. We've talked about the stateful host-based firewall. Really the only one that I don't actually have the ability to connect to very easily would be your perimeter firewall. But the perimeter firewalls are all going to be the same. Or not all going to be the same, depending on the type. So SonicWall, for instance, is a firewall as FortiGate that has a web interface, and that's how you configure that. Both also have a command line interface. Meraki is, I believe, predominantly web interface, if not only. Cisco ASA is both a GUI interface, not web-based, called ASDM. It's a GUI interface, or the command line interface. So you're going to get into firewalls. You probably will be doing some commands. The guys I talk to at my business that work with firewalls a bit more than I do, more specialized in particular firewalls, always seem to prefer the command line interfaces to the GUI. So, that is a personal choice in some cases, and in other cases it has a lot to do with the type of firewall you're dealing with. So that's going to complete this demonstration. Again, not exhaustive. We'll be talking about firewalls again in the security chapter, but just wanted to show you one of these additional network devices. Additionally, we might find some monitoring devices out there on the network. These would include like physical access control devices. Video cameras are typically IP-based. We're all familiar with seeing this, walking into stores, seeing the the camera's looking at us, but then also, noticing a monitor often with multiple camera views, especially in convenience stores. All that stuff is doesn't have to be, but in many cases, it's going to be IP based. Those cameras are connected into the network. Physical access control devices can be connected into the network and can be managed by central software. HVAC sensors for heating and air conditioning can also be plugged into the network for the purposes of notification. And from an environmental standpoint, it's very important that we keep data centers, server rooms, network closets cool. And so it can be a big deal to have those HVAC sensors that are reporting back. So now we're starting to talk about just kind of little devices that are connected in the network for some purpose. IoT is a perfect example of that, Internet of Things. And really the list of these is fairly expansive, not what's on the slide, but I'm just saying the number of IoT devices out there is, fairly ridiculous. I mean, anything from a Amazon Echo to a smart watch or any other type of smart device, garage door sensors. Cars can be operated through applications now because of computers that are in the more modern vehicles. Refrigerators, smart TVs, you name it. I mean, if it's connected to the internet, if it is manageable by an application over the internet, then it is an Internet of Things or IoT device. Okay, so these are highly specialized. They perform a particular purpose, but they do provide network connectivity. Now, it's not full-on network connectivity, right? I mean, like Amazon Echo, for instance. I mean, it's connected to the internet such that I can use an app on a phone to actually speak to people through a speaker that's in my house. Or, and I don't have this next one, but if I leave and forget to shut the garage door and I've got this all set up, I can shut my garage door using an app. I can start my car, depending on my vehicle, using an app. So the amount of data transfer is minimal, and the actual type of communication is going to be pretty limited to that particular device, but it's exactly what they need. It's what those devices need to be able to communicate over the internet and to be communicated to, and thus be able to control. The Supervisory Control and Data Acquisition, SCADA, which is a type of industrial control system. This has always struck me as a little bit odd, just that it's on the objectives. This is really just a type of network. It's not a network device per se, although SCADA network or ICS will include a number of unique types of components that are connected to the network. Industrial control systems are, things that run machines at a manufacturing plant. Okay, anything operating physical equipment, potentially, it's not always, but operating physical equipment at a factory, or the sewer systems and the train system. A lot of these are considered a SCADA type of architecture. So it's really just, as I said, a type of network architecture. You could go your whole life working in networking and never run into one of these. I'll just leave us with that in terms of how important is this. You need to recognize the acronym. Ironically, Network Plus has added in some things that I think are sort of out there, but they removed almost all of the wide area network stuff. I think that's a good thing for two reasons. Number one, most of that information was very antiquated. They were still talking about T1 lines, frame relay, ATM. That's not the automated teller machine. That's asynchronous transfer mode. FDDI, which is a fiber distributed data interface, which hasn't been used for a long, long time. All that kind of stuff is very rare for us to run into today. Today, for internet connectivity, the vast majority of us are going to have a cable or a DSL modem. Sure, there are still going to be companies that have dedicated lines to a provider, but the amount of bandwidth that you can get now with these more modern technologies, it exceeds the bandwidth that you can get with those. So why would you continue to use all of that? So let's talk about cable and DSL. These are the only two that really made the cut. Everything else is removed, but these are still there. So cable modem uses the cable infrastructure to access the internet. Okay, cable infrastructure is generally your ISP, and so you're utilizing them. You're getting connected through a cable modem. That's not really a modem. Modem stands for modulate, demodulate. Cable modems are all digital signals, but still, they still call them cable modems, okay? You can buy your own cable modem. You can get a cable modem from your provider. You can subscribe to a certain level of service, a certain amount of bandwidth. Whatever bandwidth you subscribe to, though, you are sharing that bandwidth with others, okay? This cable modems are a contention-based access method, which means just like Ethernet, you're fighting for access to the bandwidth. It also means that you are technically connected in a type of network with those around you that utilize the same connection for their cable modem to the ISP. So keep that in mind. Firewalls are always important, but very important, maybe even more so when you're using a cable modem for that reason. Also, you don't get necessarily all the bandwidth. DSL modems, on the other hand, that's digital subscriber line. The primary difference is it's going over the phone lines as opposed to the cable infrastructure. It's still digital signals, and it is also a dedicated line to your house or to your business. So whatever bandwidth you're paying for, that's the bandwidth you're going to get. It's between you and the ISP. It doesn't involve anybody else, and that's kind of why there are multiple variants of DSL, because you can pay what you want. I mean, you'll see DSL offered for $14.99 a month, and then when you actually look at it, you're like, oh, I get 128K down. I haven't had that in 20 years. So that's, you get what you pay for. They have multiple levels, but you will have dedicated internet. In that case, also you will be plugged into the phone jack, and then you'll have a splitter that splits off data and your phones in order to connect. Cable modems will connect with coaxial cable to the wall, and then we'll connect with Ethernet cabling either directly to a computer or to a router/wireless access point. Speaking of access points, there are some wireless devices. We're going to spend more time about wireless devices a bit later in another chapter. We'll mention these here because they are devices that are connected to the network. So the first one is an access point. We call it a wireless access point, or WAP is the acronym, because it provides access to the network wirelessly. In other words, it's got antennas, it's listening to radio frequencies, clients can connect to the access point. Now that's often not the ultimate, destination. They're probably connecting to the access point because I'm at the coffee shop, I need to connect the access point to get access to the internet. Or I'm at home and I connect to the access point to what? Get access to the internet. So the access point is pushing out radio signals and accepting those connections, but it's also hardwired into the network, and or an ISP in order to gain you access. All right, so this gets confused, and like I said, we'll cover it more when we get to wireless, but I can't tell you how many times you just hear the term Wi-Fi, and people are using the term, and it's okay because they're not technical. They're using the term and they don't necessarily know what they're meaning. Okay, the term Wi-Fi is 99.9% of the time my laptop, tablet, smartphone connected to an access point that is then connected to a hard line, cable, DSL modem, other Ethernet network, that kind of thing. All right, access points have to be configured, and they'd have to be configured individually. In a home, this is usually not a big issue. We can have one access point. It can, facilitate wireless connectivity throughout the house. No big deal. But in business scenarios, there's a coverage limit to these radio frequencies. And so a lot of businesses will have multiple wireless access points. And in that case, we really need a wireless LAN controller to be able to centralize the management of those access points. Otherwise, I'd have to individually configure each one of them. Printers aren't necessarily wireless, but I just threw them in here and said wired or wireless. A lot of today's printers are wireless. In fact, the vast majority in a business are probably wireless. Regardless of if they're wired or wireless, they're connected to the network. It's just the architecture that they connected to. Are they connected to Ethernet? Are they connected via Wi-Fi? All right, and that's how we are going to send print jobs, as opposed to the old days using LPT ports, and even USB ports is old now. Now it's typically all done over the IP network. In this last topic, we're going to be looking at data center architecture. This represents new content for the N10008 exam, and is in regards to more data center and enterprise level networks and how they are arranged. So for a long time in networking, we had the concept of building the network in tiers, because doing so is going to allow us to separate the logical functions of the network and allow us to target specific hardware, specific software in certain areas. Okay, so for example, you don't want to consider a switch that's designed to permit users to access the network in the same way that you would consider a switch that's purpose is moving traffic through the network core. So the three-tiered model is actually one of the most classic and still used models for network architecture. Probably the very first thing you need to understand is that in addition to be calling a classic model, it's also referred to as a hierarchical network model. Regardless of what you call it, though, it's built in 3 layers. The access layer, which is closest to the users, the distribution layer, where you have policy-based connectivity, and then the core layer. Now, different names are used sometimes. Okay, so core layer can also be called backbone, which is where the high-speed switching is. The distribution layer can often be called the aggregation layer, as we see listed here, and then finally the access layer may be called the workstation or the edge layer. Okay, so regardless of which of the names, they still serve the same purpose. The access or edge layer makes sure that authorized users can access the network with ease and given pretty high bandwidth. Okay. In addition to providing a guide for like what equipment is appropriate at the layer, the three-tiered model gives us a sense of what technologies are needed at these layers. So devices found at the access layer are going to include end user devices like laptops, desktops, smartphones. Relatively inexpensive layer 2 switches, although we could potentially have layer 3 connectivity, but typically it's layer 2 switches, and then possibly access points as well. Okay, so layer 2 switching, it's using layer 2 for sharing benefits, has the ability to use layer 2 clustering as well. And then other technologies that you would find here would be technologies that you would find with switches: spanning tree protocol, power over Ethernet, possibly VLANs, those kinds of things. The distribution or the aggregation layer is going to aggregate uplinks from the access layer into the data center core. A pretty consistent trend in networking has been the fact that more and more of the data that users need to access is actually located outside of the network. More and more traffic's being sent outside of the LAN, and that's especially true now that cloud technology continues to take hold. And so the distribution aggregation layer is a pretty critical in the design of the network, because it connects the access layer and the devices inside of it to the rest of the world. So at this layer, you have high-speed routers, you have high-speed multi-layer switches, firewalls, proxy servers as well, and it's there for security, application services. That would be a proxy server. Security devices would be a firewall. But ultimately, it helps to lower the total cost of ownership and reduces complexity. Now, three-tiered is the most common, but the layers might be logical as opposed to physical, okay? Because a lot of organizations are just too small to really need a three-tiered model. So typically they'll use the alternative of two-tiered, which combines the distribution and core layer and is referred to as a collapsed core design. And again, that's done kind of for the sake of simplicity as well as to cut cost. Okay. There are a couple of other designs as well. The spine and leaf design doesn't, the classical hierarchical model is excellent for enterprise networks, but you might have different kinds of networks at certain locations within an organization. And so there might be models that are more appropriate inside a data center. Inside a data center, the traffic is going to be different. Traffic patterns are not always what is expected. And so different models can be used for different network locations. And one that's become fairly famous is the spine and leaf topology. And one of the reasons that it's gained popularity is that vendors like Cisco rely on it for new technologies that they are rolling out. Okay, so the spine and leaf design just consist of two layers, the spine and the leaf layers. Some engineers will call the spine layer the core or the backbone layer, and then you have the leaf switches that act as an access layer. So it's really just kind of a two-tiered approach with a slightly different name. When we talk about traffic types, and when the exam talks about traffic types, they're talking about traffic flow, north or south traffic flows versus east or west traffic flow. East-west traffic flow is, essentially machines, systems, whether it's VMs, what's typically VMs, or physical servers communicating with one another. That's east-west type of traffic. North-south type of traffic would be traffic up through the data center layers. Now, there are multiple locations that we have at our disposal. We just want to talk about the difference. I think we've maybe mentioned some of these or will. Branch offices are smaller offices that exist, outside of a corporate office location, but they're still part of the larger network. They could be connected via WAN technologies, or they can be connected via VPN. An on-premises data center would be in a larger network where we have racks of servers, probably storage area networks that we're accessing, but it's still on premise. Okay, we own all the hardware, we own the computing, the storage, the network resources. A co-location is where we're renting some of that from somewhere else, but we're basically just renting the machines themselves. Okay, a co-location is different than a cloud provider. Cloud provider is where the data center is outside your on-premise organization. But it's using cloud technologies, pay-as-you-go, elasticity, scalability, those kinds of things. And so not every location outside of your organization will be a cloud provider. Some of them are just considered co-locations. Now, one of the new approaches to networking that is becoming more popular, especially in light of cloud technologies, is software-defined networking. Okay, because it allows dynamic and programmatic configuration of the network. That has the advantage of improving network performance, improving monitoring, and closely, as I said, matching cloud computing. Now, it's actually been around for a long time, but it's making a big resurgence and implemented in parts of large and small networks today. And it's changing the landscape of traditional networks. A well-implemented software-defined network will allow the administrator to implement features, functions, configurations without the need to do command line configuration on individual network devices. Okay, the front end that the administrators can interface with can alert the administrator exactly to what the network's currently doing, and then through the same GUI, we can indicate what we want done behind the scenes. And what we want done, and then it happens behind the scenes. Software-defined network will implement those configurations across multiple devices. So think of just managing multiple switches through an easier user interface. Now, so directly programmable, agile, centrally managed, that's probably one of the biggest advantages, is being able to do that, programmatically configured, and also vendor neutral. Now, the key component in most SDN solutions is the controller. This is an appliance-based device that's responsible for distributing what are called control plane instructions to network devices downstream for configuration and management. And there's, to be clear, there are a lot of different approaches that can be taken to SDN, but almost everyone agrees that the best strategy is to separate the network into discrete planes or layers of operation. And that's what we see here in the architecture. So the application layer is where all the technology that involves the applications reside. Today, it's not uncommon for an application to be powered by tiny little microservices that are running as containers in virtualized cloud environments. But there are, of course, plenty of other options for powering this layer. Many of them can be more traditional, but it's where the applications live. Okay, the control layer is often described as the brains of the operation, but that's slightly inaccurate because, the administrators are still the brain, the engineers are still the brains of the operation, but you're essentially looking and using kind of a single pane of glass solution that provides the correct API calls to the controller. API stands for Application Programming Interface. So the controller turns the commands we send it into calls to network devices in order to monitor and configure them properly. And this is that north-south. This is another example of that north-south data flow. Northbound are API calls from you to the controller, and then commands from the controller to the network device are going to be southbound operations. Then we have the infrastructure layer, which actually contains the hardware and software that powers the enterprise. In that, you're going to find legacy and dated technologies often. This infrastructure is now being controlled just in a different way, but it's still the existing hardware and software. And then finally, the management layer is necessary to perform a lot of routine maintenance on the network, and so that's what that plane is for. Now, all of these layers are critically important. Each one plays an important role, and the layers work together seamlessly to get various jobs done. In this chapter, we looked at network devices. We talked about various types of network devices that are used to communicate or provide communication across the network: bridges, hubs, switches, routers. We focused in on the configuration of switches and their capabilities, the configuration of routers and the functionality that they provide on the network. But we then talked about some additional devices: cable, DSL modems, voice over IP systems, kind of a hodgepodge of devices that exist on the network and provide a particular functionality. And then finally, we looked at data center architecture, defined some new terms probably for a lot of you new to the Network Plus exam, along with software-defined networking. These represent large enterprise capabilities, but with software-defined networking, really they represent the evolution of the local area network.